and thank you all for being here. I'm Richard Küng, and I'm delighted to take you on a small guided tour into the quantum realm for the next 15 minutes. And the results I'm going to talk about today are joint work with another institute of technology, as well as two partners in industry, namely Amazon Web Services and Google AI. And to start it off, I will only give the briefest introduction about quantum computers conceivable, just barely enough to motivate the main star of this talk, which are the aforementioned quantum-to-classical converters. And I will try to set the stage, convince you that they are important before telling you how you could actually build such a thing. And then I will segue into three applications that I find quite interesting that actually might lead us to near-term advantages with the quantum computers we have today and in the near future. And then we will wrap up. So what is a quantum computer? Conceptually speaking, the idea is very similar to an ordinary computer, like the laptop we are all using now to do these virtual events, but there's a small twist. These fundamental carriers of information are intended or designed to be as small as technologically possible. That could be, for instance, individual single ions in a one-dimensional trap, each of them carrying one bit of information. That could be photons, the smallest quantum of light flying through an optical waveguide, or it could be minute superconducting circuits on a quantum chip that is stored in a dilution refrigerator. And the important takeaway message is that this is not the natural next step of chip miniaturization, but an attempt to build a fundamentally different type of hardware. Because these fundamental carriers of information are so small that their world is governed by the laws of quantum mechanics. And those laws are radically different from the macroscopic physical laws we experience in our own world, and ultimately the laws that we use to build our next generation supercomputers. And so instead, these quantum computers are designed to solve and compute certain problems exponentially faster than any conventional hardware ever could. But at the same time, they turn out to be much, much worse for actually most of the computational tasks we could ever be interested in. And so you should really view quantum computers as co-processors that have the ability to empower existing computing architectures in specific tasks. So a useful analogy is, for example, a graphic card in your laptop that is a special purpose coprocessor that helps your laptop resolve graphics, but not much else. But let's go ahead and envision such a quantum empowered computer where we have an ordinary conventional hardware together with a quantum processor as a coprocessor. And when we view the thing as a whole, we will see that we have to start in the classical world. This is our world, the macroscopic scale. And when we want to tell the quantum computer to compute something, we have to transfer this set of instructions into the quantum realm, into a language that the quantum computer understands. We then have to let the quantum computer carry out its computation in the quantum realm and produce a quantum mechanical output. And afterwards, we somehow have to be able to read out the result of the quantum computation and transform it back into information that we on the macroscopic scale can access, like strings of bits. And as you can see here by the black line, there's two information transmission bottlenecks here. And the first one is essentially a quantum hardware design problem. And it shouldn't surprise you that because quantum mechanics is complicated, quantum hardware design is a bit harder than conventional chip design. But I'm also proud to tell you that this is actually one of the core strengths of our institute, the Institute of Integrated Circuits. And if you're interested in that aspect of the information transmission problem, then please talk to my amazing coworkers, because I want to talk about the converse relation, the readout problem. How can we take the output of a quantum computation that is stored in these minute information carriers and convert it to something that makes sense to us, or at least to our computers? And it turns out that this readout problem is plagued by several quantum mechanical effects that you might have heard about. For example, the Schrödinger's cat phenomenon, the collapse of the wave function, or the observation that in quantum mechanics, God attempts or actually plays dice. And it turns out that these quantum mechanical effects all conspire to make the readout problem surprisingly challenging. And in fact, it is an actual bottleneck that can completely negate perceived quantum advantages if you're not careful. And during my stay at Caltech, where I was doing research before I came to Linz, we decided to tackle exactly this bottleneck problem. And we came up with a new, efficient, and reliable way to convert the output of a quantum computation, or more precisely, or more generally, an actual quantum system into a classical representation comprised of bits that we can work with on our conventional computers. And on a high level, this quantum to classical converter that we call classical shadows, illustrated here, is a delicate combination between a quantum hardware part of a quantum computer, and conventional post-processing software. And the quantum hardware is non-trivial, but it is in a precise sense as simple as it could possibly be without being wrong. And at the same time, we tried to make the conventional overhead, the classical overhead, when it comes to storing and processing the resulting bit strings, efficient and tractable in the sense that the memory cost and runtime cost only scale linearly in the size of the underlying quantum system, in the size of the quantum coprocessor. And our trademark sigil with these results is that we try hard to equip this method, or basically every method that I help develop, with rigorous performance guarantees where we mathematically prove that these quantum to classical converters have to work as intended. And in fact, we actually also managed to derive matching lower bounds from information theory that tell us that our quantum classical converters are not only reliable, but they are optimal in the sense that it is impossible to improve them substantially for certain problem instances. And so these classical shadows are now a new way to convert quantum information into classical bits and play around with them. And it shouldn't surprise you, hopefully, that this new connection between quantum realm and classical computers has a couple of applications. And one of the first applications I want to talk about is the optimization of certain difficult functions that typically tell us something interesting about nature. And this is one of the most prominent and also promising use cases or applications of the small quantum computers that we have today and in the near future. And the idea is follows. You take an interesting problem about microscopic science, like the ground state problem in quantum chemistry, and you encode it into the minimum value of a very complicated function. And this function is exponentially hard to even compute on classical computers, which is why supercomputers struggle. But quantum computers can compute them in polynomial runtime only. And so this is especially a poster child application of the hybrid approach I mentioned before, because if you have a quantum coprocessor, you can now do some iterative optimization procedure, like a first order method, like stochastic gradient descent, where each time you have to actually compute the function, you ask the quantum coprocessor to do that. And then you hope that this first order method converges. But the thing is, in each of these steps of this iterative optimization method, you have to interact with the quantum coprocessor and you're facing the readout problem. And it turns out that until rather recently, the readout problem was a very real bottleneck that presented these types of algorithms to scale up the size, the number of qubits of the quantum coprocessor. And our quantum to classical converter is designed to tackle exactly this goal. And for a concrete example that was done by the Innsbruck group and published in Nature, we could show that the original readout cost for their protocol, which was already optimized, scaled at least linearly in the size of the quantum coprocessor, whereas our results scale only logarithmically. And that is an exponential improvement in the readout cost for each step of these iterative procedures. And this quickly adds up and actually can make a difference. But when we actually now have a reliable way of transforming a quantum system, which is very abstract and difficult to handle, into a sequence of bits, we can also start playing around and do maybe a bit more creative stuff. And one thing we decided to do was a quantum version of binary classification. So I'm sure we are all in Linz. Most of you know what binary image classification is. It's the poster child of artificial intelligence, where a machine where we train a machine to learn how to distinguish two classes of objects, for instance, pictures of robot dogs from pictures of robot cats. And we decided to use our quantum to classical converters to do a quantum version of this problem, where the quantum dogs are quantum systems that belong to a topological quantum phase of matter, and the cats, the quantum cats, are quantum states that belong to a trivial quantum phase of matter. And if this name confuses and scares you, that's maybe appropriate, because quantum phases of matter are rather complicated and difficult to understand. But what this plot here hopefully shows you is that a combination of our quantum to classical converter followed by a conventional machine learning procedure like a support vector machine or a convolutional neural network actually performs quite well over a wide range of difficulties, because this x-axis roughly interpolates between very easy classification problems to impossible ones. And again, our trademark sigil is that we also provide rigorous theory support that mathematically prove that this type of curve has to occur under reasonable assumptions. So it's not black box magic of convolutional neural networks that's going on here. We actually really understand what's going on. And finally, after having shown you two applications for our quantum to classical converter, I always find it's instructive to also point out in a direction where it has to fail. And this will pilot us into some very new and I find exciting research that might lead to the first provable quantum advantage for an artificial intelligence challenge. And let me just very, very briefly try to convey the main ideas, because I think it's really exciting. What we did here is we came up with a synthesized quantum learning challenge that is intended to be very difficult for procedures that take a quantum system, convert it into classical bit strings, and then do a classical machine learning post-processing. Essentially the things we did here. We came up with a challenge that is very difficult for those types of algorithms, in the sense that we could mathematically prove that any such approach needs a number of experimental repetitions, which roughly transforms into the runtime that scales exponentially in the problem size of the challenge. And this is what you see in this log plot, where on the x-axis, we plot the size of the challenge versus number of experiments, aka runtime. And this dashed line tells you that every procedure that uses a quantum to classical converter followed by a classical protocol has to be above this line. And lo and behold, these green crosses are exactly what you would get if you would take our quantum to classical converter and combine it with a semi-decent classical machine learning model. Way above the curve, as it should be. Now, what's interesting is what are the points below, right? We actually constructed our challenge to be difficult for simple learning models, let's call them semi-classical learning models, but at the same time to be easy if you had access to a more powerful quantum computer, namely a quantum computer with a small quantum memory that you could use to store some of your results and then act on it quantum mechanically later. So if you had access to a more powerful quantum computer and not directly convert everything to classical, then the runtime required to solve our challenge is actually polynomial. And this is what the lines down here are. And the interesting twist is that these dots and diamonds are actually not hypothetical numerical values, but they are actual runtimes reported by our friends at Google who ran our algorithm. Our algorithm was just simple enough to be able to be executed on Google's quantum computer, which to this date is still the largest and most reliable quantum computer we have today. And as you can see, these actual constructive runtimes are way below the dashed line, which limits the potential of any possible classical or semi-classical method. And because this is a log plot, this is actually an exponential separation, which is what I meant by a provable exponential quantum advantage for an artificial intelligence problem, admittedly a very stylized one. We kind of constructed it to work as intended. And with this, I think this is a great tone to conclude. And let me conclude on a rather high level by trying to re-emphasize that I think quantum computing is super cool. It's exciting, but it's also difficult. Quantum computers are very challenging to build and control. And if you actually want to use them and you want to find useful applications where quantum computers really pay off, it's surprisingly difficult. But I think it's also cool that we at JKU try our best to tackle these challenges. And I think we're in good company when we do so. Thank you very much.